Hi, my name is Wang. I'm a PhD student at the University of Wisconsin-Madison. This work is in collaboration with Yuhang, Zhao, and my advisor Yea-Seul. We focused on exploring how low-vision individuals experience information visualization. Visualization accessibility has been gaining momentum in recent years. However, recent research reveals a significant oversight in a larger population, low-vision individuals. Unlike non-sighted individuals who solely rely on screen reader to read out information, low-vision individuals use various assistive technologies that aid visual inspection, for example, screen magnifier. We started with a quick introduction to 5 visual functions that characterize low vision. Visual acuity refers to how well a person can see details and distinguish objects. A low visual acuity can cause objects to appear unclear or fuzzy in a distance. Wearing glasses or contacts, squinting eyes to adjust the focus, and adjusting distance are how viewers cope with the challenge. Screen reader and magnifier are most commonly used assistive technologies to deal with it, and decreasing element size is how content generated can support. The field of view, or visual field, refers to the extent of area that can be observed when the eye is looking straight ahead. Visual field loss can be categorized into 3 types. Viewers may miss content without knowing that they missed it. To compensate, viewers will utilize the remaining visual field and check the content repeatedly. Existing approaches try to scale the content to a small range to increase the chance that the viewers can see all the content regardless of their vision loss. Light sensitivity describes a condition that makes a person shield their eyes from light to prevent eye pain. Viewers may reduce monitor lightness to ease the symptom, and tinted glasses can also help. Dark mode, which changes the content from using bright colors to dark colors, is the most useful technology that provides help. Contrast sensitivity measures people's ability to distinguish objects from their background and perceive details in low contrast senses, tested with Pally-Robinson chart. Existing technologies that support people with low contrast sensitivity including high contrast mode, inverted color filter, edge enhancement, and contour highlighting. Color vision refers to the ability to distinguish differences between light composed of various wavelengths. There are different types of color blindness. What viewers will do to compensate is using brightness and darkness of the color to distinguish them. Digital colorimeter, which can detect colors displayed on the screen and provide the corresponding numeric values to read the color, is designed to support them. Moreover, a variety of color filters are now available to modify the color on the screen to accommodate different forms of color blindness. We conduct a contextual inquiry with 11 legally low vision individuals with remaining function vision, but of different visual conditions, who use assistive technology like magnifier or screen readers daily. To situate the participants with real-world scenario, we prepared 12 real-world examples with varying topics and visualization types. The study started by asking for demographic questions. Then each participant were asked to examine 3 visualizations and instructed to think aloud while navigating the visualization. For each visualization, we first provided a description of the visualization and asked what they wanted to do with the visualization. After that, we asked participants to freely navigate visualization with their commonly used assistive technology. Once participants are done, we asked them to conduct analytical tasks we prepared. After examining all the visualization, participants were asked about their experiences during the navigation. We analyzed participants' response with the semantic analysis method. We found that the intended goal participant provided matched the low-level analytical task, and after classification, finding correlation was the most commonly mentioned goal, followed by identifying extreme values. When it comes to their free navigation, many participants began by seeking an overview of the visualization. Some wanted to assess the boundary of the visualization first, and some expected to be aware of all the elements in the visualization. Another distinguished strategy that participants applied is relying on memory and prior knowledge to understand visualization. What they typically did was memorizing the legend and patterns to avoid repeatedly checking, which can be quite time-consuming for them with a limited visible area. They may also utilize their prior knowledge to strategize their search. For example, a participant attempted to guess the museum's location regarding its level of contact, and then explore the area corresponding to this judgment to search more quickly. A few participants would infer the mapping between color and the data based on their prior knowledge. For example, a participant relied on her prior knowledge to the election result to judge which bar darkness indicate Biden and Trump, given the hardness to distinguish them due to the legend's small size. Some challenges in reading visualization occur due to the assistive technology the participants were using. Participants use various kinds of color inversion software to adjust for their light sensitivity, contrast sensitivity, and color blindness. However, due to the unpredictable performance of each tool, participants may utilize multiple color inversion tools at the same time to warrant the inverted outcome. For example, our participant utilized multiple plugins that had different functionality to change the original legend. When the legend did not show up properly, he turned one filter off to make the color in the legend show up, which, however, made the text less distinguished. The inversion results do not always deliver the preferred result or provide coherent results across participants is another problem. For example, a bar chart did not invert it correctly for one participant's color inversion tool, with only inverting the text in the visualization, while some software used by another participant was able to invert the background while also change the color of the bars. The default zoom level of the magnifier that participants used in general was not always optimal for examining visualizations. They expected different levels of zoom for different visualization types and different tasks, and thus they also have a need for easy configuration for zoom level. Participants may simultaneously manipulate both screen reader and magnifier. For example, a participant uses a magnifier when he reads a title, which is larger in font and shorter in text, and then uses a screen reader to read the paragraph describing the visualization, which was smaller in font and longer. Similarly, when there are plenty of text labels in a visualization, participants will prefer screen reader more than magnifier. And thus, they expect the screen reader and magnifier work together more seamlessly. Challenges can also come from the design of visualization. All participants made comment about grid line and tick marks, mainly about their thickness and lightness in color and their sparsity. Denser tick and grid line are always expected to improve the possibility of having a grid line in the zoomed-in view to support them in tracing data points to read values. Creating nearby labels to infer the value of a specific data point is another way to compensate. For example, a participant can simply drag the mouse cursor to the nearest label instead of tracing all the way to the y-axis to know the value. While participants describe their challenges as a color problem, the underlying cause was often the low contrast that the colored elements create with the background. A grayish color can cause difficulty for participants to recognize. The gray dot, the light grayish bubble, and the overlaid bubble, the gray dashed line all cause missing or wrong understanding. Insufficient contrast difference, of course, can cause misreading directly. Some participants were not able to distinguish sections in a pie chart that use similar colors and recognize several slices as one when read it. Clustered marks can also be challenging to read. Many participants find it hard to discern different lines when they are too closely distributed. Perceived contrasts also interact with other attributes of the objects. For example, without the ability to see the red and blue due to color blindness, a participant could tell the difference between red and blue by their darkness when she looked at the bars. However, she couldn't tell the difference when she looked at the legend due to its small size. Some schemas to organize data points, such as sorting, support visualization reading by providing some structures for navigation, while certain predictable structure can aid participants in reducing navigation cost. Unexpected chart organization can lead to confusion. For instance, when the y-axis was positioned on the right-hand side instead of the traditional left-hand side, several participants struggled to locate it. Other elements, beyond the basic chart elements, were easily missed by many participants because they were often small in size as well as unexpected. Thin connecting lines between marks and labels to indicate the association are especially important but easily missing, and consequently can cause wrong understanding due to the nature of linking marks with the nearest label. Some chart types, like bar chart and pie chart, are more accessible and easily navigable because of their visuals, mainly come from thicker and heavier ink. Different analytical tasks can cause different challenges to participants. Participants generally found tasks such as clustering and determining range to be relatively easy without involving seeing details. Conversely, searching is time-consuming due to the time investment being proportional to the number of data points, and thus, sorted data provides help to quick navigation. Tracing from and to the access, and comparing among data points is hard due to the limited visible area, and thus, duplicated access and abundant available grid line are essential to help participants. To support reading values, several participants also suggested the tooltip feature. While universal guidelines strive to accommodate a wide range of visual conditions and situational factors, they may not always sufficiently cater to everyone's unique need. Furthermore, the existence of poorly designed visualizations that are not guaranteed to follow the guideline is inevitable. Based on our observations, we propose the development of a personalized tool that would re-render visualizations to suit each user's specific need. As a first step, the tool should understand the viewer's visual condition to accommodate and parameterize them to systematically re-render the visualizations. We envision the tool can elicit their condition graphically on the fly to understand their situational visual conditions with their surroundings. Then the tool should facilitate the construction of an overview, which is crucial for various analytical tasks. The tool should be capable of reconstructing the visualization to effectively communicate the layout of the visualization components and annotations, as well as the overall data trend. The details should be abstracted to ensure the data trend is visible. Clustering data by leveraging the notion of hierarchy or sampling data point would be a good option. In a zoomed-in view, the tool should provide extensive context to minimize navigation effort. For example, it should display unit and other essential information, like the visualization's description, and be easily accessible via hotkey without need cursor movement. To aid in locating specific data point, the tool should enhance search functionality, allowing viewers to either see a data point's location or automatically center the view on it upon request. Additionally, for comparison tasks, features like freezing one view while focusing on another can significantly reduce the need for back-and-forth navigation between data points. Since visualization in the wild have high chances of being inaccessible, the tool should detect the various visualization components, including ticks, grid lines, marks, and text, to enforce the guidelines. Finally, using a screen magnifier, low-vision viewers may struggle to fully leverage their visual perception for tasks like estimating magnitude or comparing marks in visualization. Since the tool can learn about viewers' specific visual condition, including their viewing field and areas of spot loss, the tool can dynamically re-render visualization to make the most of the viewer's remaining visual capabilities. To sum up, in this work, we investigate the strategies that low-vision individuals apply to understand visualization, and discovered that they were not provided with sufficient support to accomplish the goal of reading visualization. After contextualizing our findings with existing guidelines, we envisioned a personalized tool to support them. Future work could explore low-vision individuals' interaction with more complex and advanced visualizations, such as sunburst charts and network diagram, where familiarity with structure is typically lower. In-person studies that investigate physical adjustment strategies in addition to using digital assistive technologies are also worth further exploration. Future studies could also control each visual condition accurately through simulation or recruit participants with similar visual functions to better understand how each visual function impacts visualization reading. Thanks for your attention.